welcome to the lecture of this finite volume method. Now, another important parameter which comes into the picture is the calculation of diffusivity, or rather interface diffusivity. So, in our equation system or the discretized equation system, we have written these diffusive coefficients like gamma E, gamma W, gamma S, gamma N, gamma S, like that. So, these are actually the coefficients that belongs to the phases. So, these diffusivity coefficients are at phase. Now, the thing is that we have certain information which are actually at the, so if you again look at this cell corresponding stencil, this is my C, this is my east, north, south, west, and the faces like this W S. Now, it is important when this gamma actually or gamma phi, it varies with position. Okay. And if it varies with position, which will let you to have at different values of gamma at cell center. So, you can have gamma C, you can have gamma W, you can have gamma E, gamma N, gamma S. So, at elements or at the elemental level along its centroid, you will have a different values, which when this guy, the diffusivity coefficient actually varies, and this happens when you have certain materials or non-homogeneous materials where the diffusivity coefficients are varying along the grid points. So, you have different term. The calculation of this flux diffusivity would become important, and this should be much more clear. Let us consider the energy equation. Let us consider energy equation. Okay. Once we consider the energy equation, and which case the diffusion coefficient actually represents the thermal conductivity. So, the gamma is essentially the thermal conductivity or kappa of the material. Now, if that case phi is essentially denotes the temperature and the variation of the non-uniformity conductivity, that means the kappa, if it is not uniform, if kappa is not uniform, then you have a problem. The reason is that for specially non-homogeneous material, this kappa could be varying, and once the kappa is varying, then the conductivity at different locations, that means for a non-homogeneous material, the kappa at this center and kappa at this location or kappa at this location, they are going to be different. Once that is going to be different, then assuming a equivalent diffusivity is not going to get a exact solution. So, in that case, you need to have proper estimation of these gamma at a particular cell interface. As long as they are homogeneous, there is no problem, but if it is not homogeneous, so one can actually think about a very simple approach or methodology how to estimate this. One simple is that one can, using the value of gamma at cell center C and E, one can get an estimate at phase E by some sort of an arithmetic mean, and one can write, let us say, gamma at interface E could be a contribution of gamma C plus G E gamma E. So, if gamma C and gamma E is equivalent, then there will be equal contribution, where the interpolation factor G E could be calculated as a distances between the centroid from C and E. So, which could be written as d C E divided by d C E plus d E E. So, that is how one can. Now, for a Cartesian grid, for Cartesian grid, if the interface is midway, let us say uniform Cartesian grid which we have considered so far in our discretization formulation, then the interface E exists at midway. In that case, the contribution of G E would be 0.5 or half, and gamma E could be computed as a arithmetic mean of, essentially in that case gamma E is nothing but gamma C plus gamma E divided by 2. So, it is an essentially the arithmetic mean of that. So, similarly, it is just the east phase that we are talking right now. Similarly, for the other phases one can derive this expression, and if you derive that, then for other phases the coefficients would look like the interpolation coefficient. Let us say if it is at the west interface, then the G W would be d C W divided by d C W plus d W W. In the north phase it would be d C N divided by d C N plus d N N, and the south phase it is d C S divided by d C S plus d S S. So, it takes care of the distance between this point and the distance between this point. So, distance from the cell center C to the phase E and from phase E to phase cell center of E, that is what it takes into consideration. And similarly, other phases, distance between the center C to the phase west and from west phase to W center, which will get you the coefficient of G W. And when you consider the north element, it goes from C to north phase to N, that will get you the interpolation coefficient for the north, and from the south center to south phase and south phase to center of the S, that will get you the coefficient for the south phase. So, essentially it is sufficient to calculate all these coefficients at each surface points using the information you have at the element level, and sometimes one can use the volume interpolations also instead of this distance interpolation. So, it essentially takes care that thing, but there would be one this distance interpolation, this is the distance based interpolation, it can have problem, or rather it can be incorrect in some particular cases, like that, where, or rather one can say that this distance based interpolation can lead to some sort of an incorrect results when there is a sudden or abrupt change in conductivity. If kappa changes abruptly, then this kind of distance based interpolation will have a problem. So, in that case you need to have an alternative approach, and sometime people use some sort of a, instead of this arithmetic interpolation, you use some sort of a different interpolation. So, to get that, let us consider this one dimensional element. This is C, this is west, this is east, and these will be the distances. So, this distance is delta x w, this distance is delta x e, and this is the west face, this is the east face, and this is also delta x c. That means that is the distance of that particular element. Okay. Now, you have conductivity or the diffusivity, or you can write the diffusivity gamma c, gamma e, and gamma w. So, you have all these diffusivities which are stored at the center of these elements. Now, in this one dimensional analysis, we are assuming there is a non-homogeneity of the diffusivity. So, if there is a non-homogeneity of the diffusivity, one approach, as we discussed, one can do this kind of arithmetic interpolation, but this arithmetic interpolation may lead to some problem when there is a, sudden changes or abrupt changes of diffusivity. So, what one can analyze looking at the diffusion equation, let us say at east face, if we write the equation from this simple 1D model, this is the 1D stencil. So, if you write that thing at that flux, it is equivalent to writing phi c minus phi e divided by del x C e by gamma c. So, the diffusive flux at east face, one can write that, which is also equal to phi e minus phi capital E divided by del x E capital E by gamma E, which is also equivalent to writing phi c minus phi e between this cell and that cell divided by del x C e by gamma c plus del x E e by gamma e, which is also writing phi c minus phi e divided by del x C e by gamma e. That means, what we are trying to write here, that at this particular interface, the calculation of the east phase flux. So, the east phase flux one can represent using the information available at the cell center C, using the available information at phase E, and then the distance which would be used is this much, which is delta x C E and gamma C, or equivalently one can write the slope phi at this phase E minus the cell center value at E, but in that case the distance which would be used is this much, which is E capital E and by gamma of this cell, which is also equal to or equivalent to writing phi C minus phi E by taking consideration of both the distances or some sort of a distance mean here in this particular terminology, C E by gamma C, E E by gamma E, and the same terminology if I use the flux value at cell center of this, then it would be the distance of C E by gamma E at the flux level. So, hence the effective conductivity or diffusivity, whatever you call it, effective diffusivity becomes del x by C E by gamma E, del x C E, that means the distance between these two cell center equivalent to del x C small e by gamma C plus del x small e E by gamma E. So, if you look at this particular system or the expression, from there one can write the effective conductivity is like that, which is nothing but writing 1 by gamma E equals to 1 minus G E by gamma E plus G E by gamma C. Okay. Now, this essentially looks like an harmonic mean. So, the previous case which we have derived, that was the arithmetic mean, but in this case this gives rise to the harmonic mean. So, if you look back, this particular case was, so the expression if you write down, so the interface diffusivity, for interface diffusivity there are two options. Simpler option A, one can use some arithmetic mean expression, which is essentially writing like gamma E equals to 1 minus G E gamma C plus G E gamma E, where your elements are sitting C, E, west. So, this is the interface of E, this is the interface of W, and this guy will have gamma E, this guy will have gamma C, this guy will have gamma W. So, at the east interface you can get the arithmetic mean like that, or one can write the second option, which is the harmonic mean. That means you write 1 by gamma e equals to 1 minus G e by gamma e plus G e divided by gamma c. Now, as long as there is not very much non-homogeneity in the system, then arithmetic means would yield the proper results. But if there is a non-homogeneity and along with that the changes of the diffusivity is very sharp or abrupt across these cell interfaces, then one may choose to use this harmonic mean. So, the message here is that, so both the cases, let us say for uniform Cartesian mesh, if E is at the midpoint of C and E, then G E would be 0.5, which will lead the arithmetic mean would be gamma E is gamma C plus gamma E by half, or harmonic mean it would be 2 gamma C gamma E divided by gamma C plus gamma E. So, in the harmonic mean gamma E is like that. So, this one can obtain if this interface lies in between element C and E, and that is only possible when that sits there in the halfway through. So, the message here is that, so essentially the harmonic mean has some sort of an advantage over the arithmetic mean. Now, once you look at the applicability, all this interface diffusivity calculation will be important once you have some non-homogeneity in the diffusivity along the elements. If there is no non-homogeneity, if the material is homogeneous or the properties of the diffusivity along this across the cells they are homogeneous, then there is no requirement of considering this kind of surface the straightaway linear interpolation at the surface would be handy. Now, when there will be a non-homogeneity, essentially that means the gamma, this gamma is varying from cell to cell, that means this is a function of space. So, from one location to another location gamma varies. So, every cell element or the finite element, they will have a different values of gamma. That time one can adopt either of these two approaches, either arithmetic mean or harmonic mean. Both of them should yield similar results, but being said that harmonic mean has some advantage over arithmetic mean, or alternatively one can say when the harmonic mean is more preferred over arithmetic mean is the following. When your no matter you have a non-homogeneous system and your diffusivity is changing in space, top of that, if across this cell interface, let us say any of this interface E or W, the change of this diffusivity is very abrupt or rather sharp, that means between gamma C and gamma E or gamma W, gamma C, there is a huge gradient which exists. That kind of situation or the situation which arises those kind of condition or the problem, if you use arithmetic mean, then it can lead to some sort of a incorrect result. In those kind of situation, it is always preferred that you use the harmonic mean, which can lead to better interpolation of the surface or interface diffusivity. So, these are the conditions where one should have to have the calculation of the surface diffusivity, and we will stop here today and carry forward from here in the next lecture. Thank you.